This Langer line generally what its tail. So, its tail generally the one point which is yield stress point along horizontal axis, and similar yield stress point generally he consider in ordinate also vertical axis. Let us consider this is yield stress value. So, he connected this two yield stress point, one is horizontal axis and another one is what is called vertical axis. What I am telling, understand. So, you see this line was developed by Langer. So, that is why it is called Langer line, what is called Langer line, or sometimes it is called also yield line, Langer line or yield line. This you should keep it in mind. So, these 5 different generally failure criteria for fluctuating types of loading in case of fatigue analysis is popularly used. How it is, everything in details we will discuss one by one. So, you see here this yield line, whatever the yield line which is connecting this yield stress and yield stress point in vertical and horizontal axis, this is generally called the limit on first cycle of stress. This is generally called limit on first cycle of stress. This you should keep it in mind. Why this is called first cycle of stress? Because if a part yield, that means if a part subjected to a, you can say, a stress value whose magnitude is more than its yield stress value, then what happened? It has failed, that you know. That means it is regardless of its safety in fatigue. This you should keep it in mind. Once a body have a stress value which is more than yield stress value, that you can say, that means once a body is yield, then it has failed. Here generally this fatigue safety related issue is not then taken into account. This you should keep it in mind. So, that is why it is called the limit on first cycle of stress. Now, this whatever the different curve I have shown, okay, this curve generally we can write in terms of some equation. In terms of some equation, in the sense how that I am going to show, then it will be very clear to you. Let us consider little bit I am explaining, then it will be more clear to. So, you know this is SA, this is SM. Now, let us consider this is your endurance strength and this is your let us yield strength. So, the what is called Soderberg line tail, it generally represent what it is called, it generally represent connecting the point endurance strength and yield strength. Now, what is the equation of this straight line? Let us consider I am taking a point A. So, this A point is has a, let us consider which is lying over this line AC and S yield. Let us consider this as a value which has SM horizontal axis and S amplitude. Okay. Now, let us consider this is our point 1, this is our point 2, okay. This is our point 1, this is our point 2, and this is A is the point. Based on this thing we want to write the equation. So, for writing equation of a straight line, if there are 2 points are there, so what are the equation form we know? We know if the equation is, let us consider this is your x axis, this is your y axis. Let us consider this is 1 point, this is another point, 1 point, this is 2 point. So, what happens if we take any point in this straight line x y. So, what are the equation form we know, that is your x minus x 1 divided by x 1 minus x 2 is equal to, you can write y minus y 1 divided by y 1 minus y 2. This form generally we can write, correct. So, how this Soderberg equation is coming into SA by AC, SM by SY, that I am going to show. So, here you see x, here you can say x is SM, okay, and x 1 is what? x1 is, you can say here 0 comma SE, S2 is what, you can say S yield comma 0. These are the things you should keep it in mind. So, point 2 is S yield comma 0, point 1 is 0 comma AC. So, SM minus 0 divided by, I am just writing how this equation is coming, that also you need to know, that I am just showing. So, this divided by x1 is 0 minus, you can write as S yield point, this is equal to, you can write as y, means you can say amplitude, minus y1 is SE divided by, you can say SC, minus y2 is 0, because this y2 is 0. This you should keep it in mind. So, from this what you can write, SM divided by SYT, there will be a minus, is equal to, you can say SA divided by SE minus 1. So, I think there is no problem. So, from here what you can write, from here you can write as SA divided by SE, this minus, if you take that side, that SM by SYT, this will be equal to 1. So, this is called Soderberg equation. So, how this Soderberg equation is coming, this idea you got, correct. So, for remembering purpose, what you can say, generally M, for M case generally is horizontal line, there Soderberg point is generally in yield stress point, that is why SM by S yield plus SA vertical line, here it is started from endurance strength, SA by AC. So, that equation is shown as Soderberg line. So, similar way for Goodman line, generally we can write as SA by AC, here also this line is started from endurance strength and it goes to what, ultimate stress, and it goes to ultimate stress. This you should keep it in mind. So, if you take a point here, SM and SA, SN and SA, and let this is your point 1, this is your point 2, you can also rewrite the equation which will be coming as SA by AC, SM by S ultimate. Always you should keep it in mind, for horizontal axis as the cutting point is ultimate, that is why M by UT, and as it is cutting in vertical line is what is called endurance strength, that is why SA by SE. This you should keep it in mind. So, another equation generally which is shown here, you see this equation is called Gerber equation, this you should keep it in mind. This equation here generally it shows that both a parabola and ellipse have a better opportunity to pass among mid-range tension data and to permit quantification of the probability of failure. So, that is why this Gerber failure criteria and ASME elliptical line is come into picture. This you should keep it in mind. So, you see, because here you see this failure data point which is based on experiment, you can observe that. So, if you draw here a elliptical line or parabolic types of line, so this you know these things, endurance strength to this ultimate strength, this is the ultimate strength value, this line is called generally Gerber line. So, this Gerber line, if instead of a straight line, if we draw a what is called parabolic types of line, this is a parabolic line, Gerber parabolic line, then what happens, maximum points are failure point, these are all failure point based on this Goodman line. Whereas, if we consider this line Gerber line, then this point is come inside that line. So, I have already told you, if the point come inside the line, then that is generally safe line, safe point. If it is outside that line, that means if it is outside, like this point is outside this Gerber line, so this point is failure point. So, this Garber line generally, that is why I have written here. So, if we draw a parabola or elliptical line, a better opportunity to pass among the mid-range tension data and to permit quantification of the probability of failure. This you should keep it in mind. That is why this Garber equation, which is SA by AC and SM by S ultimate whole square, this you should keep it in mind. What I am telling, understand? So, this equal to 1. Here we have not yet considered the factor of safety. For actual design case, what we need to do? We need to use factor of safety, that I will show in next slide. Similarly, elliptical equation also we can write, that is called ASME elliptical line. That ASME elliptical line generally, you know, it is starting from endurance stress and it goes to yield stress, and elliptical equation, you know, x square by a square plus y square by b square equal to 1. That is why here this is the things, that means SA by AC. So, every case you see the line start in vertical point endurance system. That is why ASA by AC is available in every equation, this is available. So, as it is a elliptical line, so elliptical equation we use SA by AC square, as in SM by S yield, this we use for along horizontal axis, this term generally we use, because elliptical equation is x square by a square plus y square by b square is equal to 1, this you know, correct. So, that based on this thing generally this equation, ASME equation is coming into picture. And another equation also I have shown, that equation is drawn generally, this is called a Langer first cycle yielding criteria. Langer first cycle yielding criteria, what is this point? It represent here, this along vertical axis it is started from yield point. Similarly, along horizontal axis also it is started at yield point. So, once we join these 2 points, whatever the line we got, this is generally called Langer first cycle yield criteria. Why it is called first cycle yield criteria? Because if a body is subjected to yielding, that means if any point outside this line, then what happens? Fatigue analysis further is not required, that you can say. That means it is already failed. This you should keep it in mind. Okay. So, this equation how it is coming, SA by SM is equal to S yield, and because you see here SA by S yield will be there plus S m by there also S yield will be there, this equal to 1. So, if we take common this S yield, this will be SA plus SM equal to, you can say, S yield point. So, that is why this equation is coming as this you should keep it in mind. So, these 5 different failure criteria which is popularly used to design a structural component which is subjected to fluctuating types of loading, this you should keep it in mind. Now, previous case we have not considered the factor of safety. So, we consider the point is lying on the what is called different failure criteria line. Okay. But in design case what we used to do, we generally use some factor of safety. So, then once we use factor of safety, then this amplitude will be written as, you can say, factor of safety into, you can say, allowable endurance, allowable amplitude of the stress, you can say. Similarly, SM we can write as factor of safety into allowable mean stress of the component, this you should keep it in mind. So, here this always you should keep it in mind, this factor of safety is generally greater than equal to 1, that you can say. It should be more than 1, because you see then only you see this allowable stress should be always, you see it should be always less than the point lying on the line. That is why here I have written S A is equal to, you can say, whatever the S A sigma A equal to, or you can say allowable types of amplitude of stress equal to your, you can say, amplitude of the stress on the line divided by factor of safety n. So, similarly, this also we can write mean component, we can write at S m by n. This you should keep it in mind, because generally let us consider this is endurance strength, this is your yield strength. Okay. So, for this case if a point lying on the line, that point is represented in terms of SM and SA, but generally this is the, you can say, extreme point. That means, if the point in this case if the factor of safety 1, that case generally you can say this is your SM and SA is allowable stress itself. But in case of fatigue analysis, generally we consider some factor of safety which is more than 1. This you should keep it in mind. So, for that case generally our stress value should be inside this line. Inside this line means in the sense sigma m and sigma a, this you can say. You can say sigma m and sigma a, which is you can say less than SM and SA, that you can say respectively, this you can say. So, that is why always you should keep it in mind, sigma m is equal to SM by factor of safety, this you should keep it in mind. So, and sigma a is equal to SA by factor of safety, this you should keep it in mind. So, based on these things, generally what we got in previous equation, that is your SA by SE plus SM by S yield, this will be equal to 1. Now, if we consider this factor of safety, then SA here we need to write as n into sigma a divided by SE, SM we need to write as n into sigma m divided by S yield equal to 1. So, if this n is taken common, then what happens, this equation is converted to this you should keep it in mind. Similarly, for Goodman equation, this equation will be coming as like this. Similarly, for Gerber equation, you see instead of SA, n into sigma a is there, instead of SM, n into sigma m is there. For ASM elliptical, this equation is coming like this. Similarly, for Langer static yield criteria, this equation is coming like this. These are the things you should keep it in mind. Okay. Now, here one things you should keep it in mind, there are generally two ways to proceed this typical this fatigue analysis. What are the two ways we can proceed this fatigue analysis which is subjected to fluctuating load? In one method, what we can consider, we consider the fatigue failure is occurred. So, for a particular SM and SA value, fatigue failure is occurred. So, based on this SM and SA value, what we can do using different equation from Soderberg to, you can say, ASME elliptical line, what we can consider? We can calculate either factor of safety value as well as what it is called dimension, size means dimension of that structural component. So, in one method what I have told you, assume that fatigue failure is first occurs, then here what happens, using whatever the failure criteria we use, any one of the equation we can use, based on these things, based on our that equation value, we can determine what is the factor of safety value and what is the dimension of the component. So, depending upon our task, this is one way you can solve the problem. Okay. Now, other method, generally first of all we need to draw a load line. What is load line? First of all, that we need to know. Load line means this is your origin. So, load line means, let us consider we have a SM and SA value. So, if we generally connect this that point we are getting in a structure, let us consider this is our A point, connecting this 2 point OA, and if you extend these things, whatever the line we got, this is generally called load line. So, this load line generally it's cut different failure criteria line. What happens, different all the it generally cut different failure criteria line. If we draw this line, all the 5 line it will cut. So, here another method generally it is considered whichever the first line its cart with this load line, that failure criteria we need to use and determine the what is called rest of the things. That based on this you can say maximum stress and minimum stress value. First of all you need to find out what is SM and SA. So, based on this we need to draw a point A. So, this point we need to connect with the origin, and if we extend it, this line generally cut different failure criteria line, different failure criteria, like this is AC, this is generally S yield, this is Goodman, what I am telling, understand. So, different failure criteria it is cut. So, depending upon our consideration of failure criteria, we need to use that failure criteria line, and we need to design our structural component. That means, there also we need to define our factor of safety, we need to find our what is called dimension of that structure. So, this detail I will discuss in subsequent what it is called lecture come subsequent slide itself. This you should keep it in mind. So, here one thing you should keep it in mind, it is observed that for design purpose Goodman equation is more popularly used, because for design consideration, though you see you can see this Soderberg equation is more conservative, but what happens, more conservative than Goodman equation, but Goodman equation generally you can say which is more popularly used, because it is you can say it is generally just below the whatever the different point we have considered for drawing what is called different what is called chart based on what is called ratio of SM by S ultimate and A by AC. Similarly, based on strain value, whatever the different point we got, it is observed that generally this Goodman line is below those point, whatever the point are there, and below that Goodman line another line, that is Soderberg. So, Soderberg is more conservative than what it is called Goodman, because Goodman it's already account for all the point which is outside of this Goodman line itself. What I am telling, understand. That is why what happens, Goodman line itself is a safe line. Further another line is there, that is called Soderberg line, what I am telling, understand. That Soderberg line is further more conservative. That is why if you use Soderberg line, then what happens, you will be in more safe side, but what happens, their costing and other things, dimension and other thing of your structural component will be, you can say, higher side, that you can say. So, that is why you can say Goodman line is widely used as a criteria of fatigue failure when the component is subjected to what is called fluctuating types of loading, where there is a mean stress value as well as a what amplitude value. This you should keep it in mind. What is the other reason of using Goodman equation? Other reason is Goodman equation is this Goodman line is safe from design consideration. I have already told you, generally Goodman line is below the all failure point which I have shown in first figure 1 itself. Whatever the point were there, it is already inside that failure point itself, what I am telling, understand. That is why it is a safe line itself. So, furthest safe line is not generally required. If you consider, you will be in furthest safe side, but then your dimension and cost will be increased, that you can say. So, that is why I have written it is safe from design consideration, because it is completely inside the failure point of the test data. Whatever the test data are there, it is inside those test data. That means, all the failure point generally available outside this Goodman line itself, almost all the points. That is why it is safe. And another things is, as it is a straight line, that is why what happens, these things we can use very easily, this straight line we can construct very easily compared to using a parabolic equation or elliptical equation. That is why I have written the equation of a straight line is simple compared with the equation of parabola or curve. That is why this Goodman equation is more popularly used what it is called for design of components subjected to fluctuating types of load. So, it is observed that to be in more safe side using Goodman equation or Goodman line, for design purpose generally we use another very important you can line, or you can say another very important diagram we use there, where we consider both the effect of Goodman line and both the effect of yielding line. What I am telling, understand? Yielding line means Langer line. So, considering these two effect, a diagram is developed, you can say that diagram is called modified Goodman diagram. So, you see Goodman diagram is already is a safe from design consideration, I have already told you, but generally if the what is called as in Goodman diagram we use the extreme point is ultimate stress. So, according to Langer equation I have already told you, generally if the point is outside the yielding point, there generally we consider it is already failed. That is why to incorporate those yielding effect in Goodman equation, generally a separate diagram is developed, that is called modified Goodman diagram. That modified Goodman diagram incorporate the effect of Goodman equation as well as this yield criteria effect. That is why that modified Goodman diagram is more popularly and more safely used for design a component subjected to what it is called subjected to fluctuating types of loading. So, how this modified Goodman diagram is come into picture, that related things now I am going to discuss. So, generally the component which are subjected to fluctuating types of stresses are designed by the modified Goodman diagram, because the Goodman diagram is already very popular, but what happens to incorporate the effect of yielding, generally what happens here, this Goodman diagram is modified. So, this for this reason this modified Goodman diagram is used. For the purpose of design using modified Goodman diagram, the problems are classified into two groups. What are those two groups? In one group generally the component which are subjected to axial and bending types of stresses. Another group is the component which is subjected to fluctuating torsional types of shear stress. These two group generally we use. For these two group, two different modified Goodman diagram is established. Based on these two modified Goodman diagram, generally we design the component subjected to fluctuating loading. That is why I have written here two separate diagrams are used for design purpose. So, in this diagram, modified Goodman diagram, the Goodman line or Goodman equation is modified by considering fatigue failure with failure by yielding. This you should keep it in mind. So, that is why as the Goodman line is modified by yielding line, or you can say Langer line, that is why it is called modified Goodman diagram. So, in next lecture I will discuss in details how to draw modified Goodman diagram, and based on this modified Goodman diagram how to solve problem related to bending stresses and axial stresses and related to torsional types of stresses. So, these are the references which I have used for this lecture. Thank you.